Welcome to Digital Logic Design. Throughout this lecture, I'd like to request you to pause the video whenever you need it and keep pen and paper with you so that we can solve problems to consolidate our understanding. In this lecture, I'm going to talk about XNOR gates, half adder, full adder, and ripple carry adders. So XOR gate with the complemented output is known as XNOR, just like an AND gate with a complemented output is known as a NAND gate. So it is written with this symbol. It's a circle. Inside the circle there is a dot. So X XNOR Y is equal to not of X XOR Y. So XNOR is also referred to as coincidence operation since it produces 1 when both inputs are same. In lecture 1, we already talked about a 1-bit adder. We were able to design a 1-bit adder that outputs the sum and carry the sum operation. Here we revisit the adder. So let's say we have two binary numbers, x and y. Both of them are 1-bit. So there are 4 possible combinations of the values of x and y: 0, 0, 0, 1, 1, 0, and 1, 1. So if we sum two numbers, we have a sum output and we have a carry. So let's say if we sum 0 and 0, the sum is 0 and the carry is 0. So I'm writing sum on the right and carry on the left, just like this. So if we sum 0 and 1, the sum is 1, the carry is 0. If we sum 1 and 0, the sum is 1, the carry is 0. And when we're trying to sum 1 and 1, sum is 0 and carry is 1. So if we convert this into a truth table, we have a truth table with 2 input variables and 2 outputs, sum and carry. As we know, the number of output variables is equal to the number of circuits we need to design. We need to write or build 2 kernel maps, one for the sum and one for the carry. And then we can sort of design the circuit. So the carry C is the AND function, and the sum S here is the XOR function of the inputs X and Y. So the circuit realization, so obviously this is a simple one, so you can do it without the kernel maps. The circuit realization of these functions is shown in this figure. So this is the sum output and this is the carry output. So this circuit that we introduced in lecture 1, which implements the addition of only 2 bits, is called a half adder. And the symbol of half adder looks something like this. So these are the 2 input numbers, and this is the sum, and this is the carry. Now, why is it called a half adder? So we've just designed a simple circuit that can add 2 binary numbers. Now, can we design a circuit that can add larger numbers using the same idea? So let's say we're trying to design a circuit that can add 2 large numbers to, let's say, 5-bit numbers. So the first number is x and the second number is y. And we're basically trying to sum 15 and 10 here. This is the binary representation of 15, and this is the binary representation of 10. So as we sum the first position here, 1 plus 0, the sum is 1 and the carry is 0. And this carry, I've written the carries of the last bit here. So since the first bit's carry is 0, I just write it here. The second bit's carry is 1, I write it here. The third sum's carry is 1, so I write it here, and so on. So why am I writing the carries here? Because when you're summing two numbers, we also need to consider the carry of the previous bit. So let's say in the third bit here, we're summing 1 and 0. We can just write 1 here because we need to consider the carry 1 that is coming from the last sum operation of the last bit. So we need to sum 1, 1, and 0 to obtain the sum and the carry for the next bit, which is also 1. So in other words, there should be a means to propagate the carry, 1 bit's carry to the next, so that we can take the carry into consideration when we are trying to sum these 2 bits. So if we go back to half adder, we see that it has only 2 inputs and it does not take into consideration the carry from the previous bit. If it did, it would have had 3 inputs, x, y, and carry from the previous bit. 3 inputs. But it has only 2 inputs. So the half adder is only considering these 2 numbers. But this makes no sense. I mean, when we're trying to add bigger numbers, because we can't just sum x1 and y1 here. We need to sum x1, y1, and the carry from the previous sum, which is x0 and y0, when we are trying to get the sum and carry of the second bit possession. So long story short, the half adder does not consider the carry from the previous bit, which is why we need to find a way to incorporate the carry from the previous bit. So the ones and zeros that I've written here. So a half adder does not consider these ones and zeros. It just sums the 2 bits. So for a bigger number, in order to find the sum and carry of 2 bits, we need the current 2 bits and the carry of the previous addition. So if we want to express it as a truth table, there will be 3 inputs. 2 bits to be added plus carry from the previous addition, instead of 2 inputs of half adder and 2 outputs, 1 for sum and 1 for carry of the current addition. So it should look something like this. So Ci here is the carry of the previous sum operation. Xi is the current bit and Yi is also the current bit. And Ci1 is the carry of the current sum. So when we sum all these 3, the carry that is generated is called Ci1, and the sum that is generated is called Si. Ci1 here will be used as the carry of the next bit operation. So to construct the truth table, now these are all binary numbers, Ci, Xi, Yi. What I've done is that I have written all possible combinations of Ci, Xi, and Yi, 0, 0, 0 to 1, 1, 1, that is 0 to 7. And in order to generate the sum and carry, I've just summed these 3 numbers. So if we sum 0, 0, and 0, the sum is 0, the carry is 0. If we sum 0, 0, 1, the sum is 1, the carry is 0. If we sum 0, 1, 0, the sum is 1, the carry is 0. Again, if we sum 0, 1, and 1, the sum is 0 and the carry is 1, and so on. So this is the truth table of a full adder. Why? Because it is also considering the Ci, that is the carry of the previous sum, whereas a half adder was only considering Xi and Yi. It wasn't considering the carry of the previous sum. So by observation, we can again see that the sum bit can be implemented using an XOR function again. I mean, you don't have to solve this by observation. You can write truth tables, one for Ci1 and one for Si, and determine that it's indeed XOR function. And we can also, so we can also determine these expressions or realizations using K-maps. So if we do that, we end up with these 2 expressions, and if we, so the Carnot map output is this expression, and we know that x1 XOR x2 is x1 not x2 plus x1 x2 not. If we apply this, we end up with this expression, xi XOR yi XOR ci. So I have shown the derivation here, how I arrive from the expression derived from the Carnot map to the XOR format. So this is x1 not x2 plus x1 x2 not, which is the xi XOR yi, and similarly we can apply XNOR here, which is XNOR y is equal to x0 y0 plus xy, which is why we can replace it with XNOR. And again, if we consider xi XOR yi as a single variable, let's say capital X, then we have x c0 plus x0 c, which looks like this. So that's why we can write x or c. So hopefully you don't have any problem with this derivation, and we cannot further convert it into another logic gate for the carry, so we can just go on and implement this in a logic circuit. So this is basically the circuit of a 1-bit full adder. So this, unlike the half adder, also considers the carry from the last sum operation. We can also create a full adder using 2 half adders and an OR gate. So here I've shown the construction here of a full adder using 2 half adders. So we might ask that, okay, the full adder that we just designed still only adds 1 bit. How does then computers add really large numbers? So the answer to this is by repeated application of this same full adder circuit, we can design bigger adders. So in order to add larger numbers, what we do is that we use a series or a cascade connection of full adders. So if we're trying to add 8-bit numbers, we need 8 full arrays. If we're trying to add 4-bit numbers, then we need 4 full arrays. So this is an illustration of a full adder that is capable of adding larger numbers. So I'm now going to explain how this full adder operates. So let's say we're trying to add 2 numbers, x and y. So x0 is the rightmost bit, or the 0th position, and x1 and y1 are the 2 bits at the first position, and so on. And xn minus 1 and yn minus 1 are the leftmost bit of the 2 numbers. So each full adder takes 1 bit of the 2 numbers. So let's say we set initial carry equals to 0. So when this full adder gets the 2 bits and the carry, it produces the sum here and sends the carry to its next full adder. So once the next full adder gets the carry from the previous full adder, it has already gotten the 2 bits that it has to add, so it instantly outputs the sum and then propagates the carry to its left. And this continues until we reach the last full adder. So the last full adder, when it receives Cn minus 1 from its adjacent full adder, it produces the sum and the carry, and the final carry goes to the beginning of the number. So the final output is Cn Sn minus 1, Sn minus 2, Sn minus 3 up to S1, S0. So that's the final output. So this configuration is called the ripple carry adder because the carry here is like jumps from one adder to one next. So at first we set initial carry C0 equals to 0, and then the carry jumps to the next adder, and then it jumps to the next adder, and then jumps to the next adder until it reaches the last adder. When the final carry is produced, it goes to the beginning of the sum. So the carry is propagated through the adders just like ripples are propagated in a pond water. So that's why it's called the ripple carry adder. So the carries that are produced by the full adders propagate to the left. In a real ripple carry adder, each full adder introduces a certain amount of delay before its sum and carry outputs are valid. So let's say the delay is delta t. So thus the carry out from the first stage C1 arrives at the second stage here delta t times later. And the carry of the second stage C2 arrives at the next stage delta t times later, and so on. So the signal Cn-1 is valid after a delay of n-1 delta, which means that the complete sum is available after the delay in delta t. So because the way the carry signals ripple through the full adder stages, the circuit in this figure is called the ripple carry adder. So this is a symbol of an 8-bit ripple carry adder. So it's kind of a pain to draw all of this when we're trying to use a ripple carry adder, so it's always better to use this symbol. So this is the symbol of an 8-bit ripple carry adder. So x0 to x7 is the first number that we're using, and y0 to y7 is the second number that we need to add, and the outputs are the last bits carry C7 and the sum bits, so S7 to S0. Notice that there is no intermediate, so we cannot get the intermediate bits, intermediate carries. So C1, C2, C3, C4, all these intermediate carries are not outputted in an 8-bit ripple carry adder. Why? Because we don't need them. 1 bits carry is only needed for the next full adder. So 1 full adder's carry out is only needed for the sum of the next full adder. That is why the intermediate carries C0 to C7 are not shown in the full adder, and they're not required for the function of the full adder. Okay, so please pause this video and try to solve this problem, and then we'll match our answers. So please pause this video. So hopefully you've been able to solve this. So it can be solved using 2 approaches. The first one is a rather naive approach, using 2 8-bit adders, 2 adders, ripple carry adders. So the first one, in the first adder's input, I'm giving A and A. So here x is equal to A, y is also equal to A. So the output of this, the first adder, ripple carry adder, will be 2A. Notice that the first ripple carry adder's output goes to the input of the second ripple carry adder. And also we're giving A. So 2A plus A is equal to 3A. So if the input is A, the output is 3A. And there you go, we've designed a circuit that takes an 8-bit unsigned number and multiplies it by 3. So let me discuss the functionality again. So we're giving to the X input the number A, and we're giving to the Y input of the adder the same exact number, A. The output of the first full adder is 2A, which is in fact fed into the second ripple carry adder's input, and we also feed A to the second ripple carry adder's other input. So 2A plus A is equal to 3A. Notice that if we need 9 bits to store the sum outputs of 2 8-bit numbers. That's why we have x0 to x8 here. So the sum of 2 8-bit numbers can be 8-bit, but it can also be 9 bits. So it's always safe to keep 9 bits to store the sum. So the sum 0 to sum 7 goes to x0 to x7, and the final carryout must also be considered, which is why it is also considered here, which is why we need 9 bits. So the key point is the sum of two n-bit numbers require us to store in an n+1 bit storage. So if we're summing two 3-bit numbers, for example, the output can be 4-bit, so we need to store the sum in a 4-bit storage or 4-bit memory. Now this is a rather naive approach. There is an efficient way to design this. So we can also design this using one ripple carry adder instead of two, and thereby reducing the cost by a lot. So what I've done here is that I have shifted the bits of one of the numbers. So let's say we have a number 70111, a 4-bit number. So if we shift the number to the left, so we just move the one here, this one here, and this one here, and this vacant position, we set it to 0, we end up with a number called 14. So left shift once means multiplication by 2. So if we want to multiply by a number by 2, we can just left shift it. Alternatively, let's look at this number, 4-bit number 1110, which is 14. So if you right shift it, in other words, we put this one here, we put this one here, and we put this one here, and in this empty bit we put 0. We end up with this number 0111, which is 7. This indicates that right shift once means division by 2. So if we want to divide a number by 2, we just need to right shift the number once, and if we want to multiply a number by 2, we can just left shift once. So with this idea in mind, we can design our efficient circuit that can multiply a number by 3. So what we're going to do is that we're still going to input a in y, in the y input, but in the x input of the adder, what we're going to do is that we're going to input a shifted version, a left shifted version of the number a. So to implement the left shift, I have set the rightmost bit equals to 0. So this is a 9-bit adder, 9-bit ripple carry adder, full adder. So to implement this left shift, I have set the rightmost bit equal to 0 and input and put the other bits of the number a from x1 to x8. So the number a is directly inputted to the y input of the adder, and the x input of the adder takes a shifted version, left shifted version of the number a. So if we left shift the number a once, we get 2a, and the unshifted version gives us a, so 2a plus a is equal to 3a. So this adder outputs 3a. So hopefully you have a clear idea what half adders, full adders, and ripple carry adders are. If you have any question, let me know, and thank you for your time.